In this video, we're going to learn about the concept of resonance. So here we've got a Lewis structure for the nitrate ion. And it's kind of arbitrary, the fact that we chose to put the double bond between the nitrogen and this oxygen as opposed to between the nitrogen and, say, that oxygen or that oxygen. In reality, if you were just drawing a structure of nitrate, all three possibilities would be equally valid, although none of them would truly explain the bonding that is present in the NO3 minus ion. The fact of the matter is that there are three equivalent resonance structures, and they are all equally valid, and the true structure of nitrate is actually um, an average of all three. And since all three of these are basically the same thing, it's exactly a perfect average. 33 and a third percent of this one, 33 and a third percent of this one, and the third resonance structure, um, 33 and a third percent this one as well. I'm just going to omit the lone pairs, but uh, you can imagine there would be two lone pairs on the doubly bonded oxygen in both of these resonance structures, and there would be three lone pairs on the singly bonded oxygens in the other two oxygens in these two structures. So important thing is the true structure of nitrate is the average of these three. And you could even say that each N-O bond is not a single bond, it is not a double bond, but it's actually a 4/3 bond. I know, pretty weird, but it's true. Resonance is very common among polyatomic ions, and it's very common among polyatomic ions with a lot of symmetry, like nitrate, like carbonate, CO3 negative 2. There are cases where there is asymmetry, like the thiocyanate ion. Um, and in the case of the thiocyanate ion, what we could do is, knowing that nitrogen can form three bonds, we could just take the lone pair here and move it to form a triple bond between the C and the N. And that would be expanding the octet of the carbon, though, because we have 2, 4, 6, 8, and adding another pair would give us 10. So what we'd have to do is take one of these bonds and move those electrons to the sulfur. And this is possible. What we would get is another resonance structure. Sorry about that one. Where the C is triply bonded to the nitrogen. Again, you should be familiar with triple bond nitrogen, right? You've seen it in some cases. This looks a lot like the cyanide ion until we add in the sulfur. And now, instead of having two lone pairs, the sulfur has three lone pairs. If you count up all the electrons, you will still get a negative charge. Now, because this is not perfectly symmetrical, you could even take it a step further and evaluate which is the more significant resonance structure. And we'll take a moment for that right now. The difference between these two structures is ultimately, does an extra lone pair exist on the nitrogen, or does it exist on the sulfur? Notice a lone pair. We have two lone pairs on the nitrogen and two on the sulfur in this structure. But when we get to here, we've dropped it down to one lone pair for the nitrogen and added one to the sulfur. So the question is, which of these two atoms, nitrogen or sulfur, should have that extra lone pair? And the answer is probably the nitrogen is the one that should have it, because it is more electronegative than sulfur. And so what we can say is that because nitrogen is more electronegative than sulfur, this structure that puts an extra lone pair on the nitrogen is probably going to be a little bit more influential in explaining the true bonding that is in the thiocyanate ion. Is it true that you have a straight up double bond between C and N and a double bond between C and S? No, it's going to be somewhere between these two. But the structure to the left is probably going to be a little bit more influential. So I hope this video has been helpful. Please feel free to leave any questions or comments in the comment section below. Thank you.